Hello, my name is Matt Whitting and I teach science in the high school level at Twinsburg High School. Today's lesson is going to be a video lesson on net ionic equations. It is primarily built for the chemistry classes at Twinsburg, which normally would cover mostly the junior class. I do have some ambitious sophomores who take chemistry their sophomore year, and every once in a while there may be a few seniors. But like I said, it's mostly the secondary education level, the high school chemistry. The lesson's on net ionic equations, and the purpose of this lesson is to kind of wrap up all of the work we've been doing prior to this with solubility and chemical reactions and balancing equations. Net ionic equations kind of show a special reaction where it forms a precipitate, and the students will see how that precipitate is represented in an equation showing the different ions. The key for the students with this video and afterwards will be learning the proper way to correctly write an ionic equation, showing the key ions that are responsible for the precipitate and eliminating out the spectator ions, the ones that are just there to kind of watch the reaction.
Today we're going to be talking about net ionic equations. A net ionic equation is basically the ions showing and forming precipitates. So, to review, up until this point we've talked about chemical equations and how we balance them with coefficients. So hopefully we all remember that when we make a compound, whether it be ionic or covalent, these little coefficients are the only things we can add to make the equation itself balance. The subscripts come from the formula building process. If we look at salt, table salt, NaCl, it's a soluble substance, which simply means that when it is added to water, it's going to ionize, or as you can see here on the slide, dissociate. And it's going to break the bond between the sodium and the chloride and release it back into ion form. So when I add the crystal form of salt into the water solution, it dissolves and we no longer can see the crystal forms. We know the salt is still in there, but it's not in the same form. It now is in the ion form. So as you can see down here in the bottom left hand corner, the salt in the solid form has been ionized into the ion forms. And these AQs, if you remember, stand for aqueous, meaning that it is dissolved in solution. Another example would be here when we take a reaction between two compounds, two ionic compounds, and we mix them together. We have this lead nitrate solution and this sodium iodide solution, and we mix them together and it forms us this bright yellow precipitate. That's what we're going to talk about today, this type of reaction, which is known as a double replacement reaction. And the general formula, if you recall, was AB plus CD, and it's going to switch in the cations, if you recall, which are the positive charged ions, are going to basically switch places, giving them the new ion. So we have our A, which is the cation, is now going to be with the D, leaving behind the C with the B. Make that a better looking B. Okay. One thing to remember here is that when you do this, you always need to make sure the cation is first. So in this case here, that's my positive charge, and this is my positive charge. Now, with what we said, we're talking about net ionic equations. For net ionic equations, there's a few rules you want to follow. Step 1, you always want to write a balanced molecular equation. Then you go to your solubility rules and you predict, is it going to be aqueous or solid. Step 2, then you do a complete ionic equation. And it's important to know here that if you have an S, that is going to stay together, it's not going to ionize, and if you have an AQ, it will break apart into their ion forms. Step 3, then, you'll cancel out the spectators, as I say, the ions that aren't really involved, they're just there watching the reaction, and it leaves behind then just the ions that are responsible for forming that precipitate. So, if we go back to this guy here, we have PbNO32 plus 2NaI gave us the PbI2 and the 2NaNO3. So, step 1, the reaction we said was PbNO32 plus NaI. And we had a 2 in front of that. And that gave us the NaNO3 with a 2 plus the PbI2. And we said this was the solid, this was aqueous, we know these two were aqueous, and we know this is aqueous. Step 1. For step 2, we want to break them apart into their ion forms. So, it becomes Pb plus 2 aqueous plus this coefficient up here tells me now, coefficient here, NO3 minus, so that subscript becomes a coefficient, it's aqueous as well. Here we have a coefficient out front, so it has to go to both, Na plus 2I minus. Here we have the same setup, so 2Na plus 2I minus. All of these are aqueous, of course. It can be a little tedious writing the AQ all the time. This is the only step that I won't count against you if you don't add the AQ. For step 3, it's an absolute must. You must have the state of matter because that's the final product that we're trying to get to. And then last but not least, we said if it's an S, it doesn't break apart, so we leave that just like we see it. So that's step 2. Step 3 then, we're going to cancel out our spectators. So our NO3s cancel, which should be right here. There should be an NO3 minus. So our NO3s cancel and our NAs cancel, leaving behind our Pb plus 2 aqueous form, must have that in there, and our 2I minus aqueous form. And that gives us our PbI2 solid form. So, net ionic equations are 3 simple steps. Step 1, our balanced equation. Step 2, then our ions in the ion form canceling our spectators, and then step 3, the actual finished product, showing the 2 ions that were responsible for that bright yellow substance, that bright yellow precipitate reaction. Write down any questions you have, bring them to class tomorrow, and we will work on figuring out what we need to do to make you understand net ionic equations.